can't
and
see
yet,
me, I can't see you.
we
Is
are.
that exactly what it says?
Yeah, sure.
Okay, let's talk refraction.
This shit doesn't make any sense.
Awesome.
Get out.
I've stared at this for forever.
Oh no, is it okay? Yes, what's your question?
If your camera's in the water, does it look the same? Like it's the same little displacement between the pencil?
Yeah.
Because you're.
It floats.
Yeah, but when we did our experiment today, it was different if you looked
No,
at the
it'll
curved
look
part.
different in the water.
How about go swimming?
But if it sinks, it replaces. What?
Okay.
Down here.
So here's a good example of the law of reflection. You can see the angle of incidence is this, from this center line, this normal to the surface here, to this incident angle. And here's your reflected angle. And if you have this nice and straight, you can see those angles should be equal. So if you make the angle a little bit bigger by moving the incident ray, like this, you can see it bounces off at always an equal angle. Now, if instead of this shiny surface, like a mirror that we've had for the reflection, if we put something translucent, meaning something light can pass through. So here, this ray is going through air, but once it enters into our little piece of plastic, I think this is lucite, you can see it bends a little bit. But you also should see very faintly, there's still a reflected ray, and as you turn the light, the source of the light, you can see that there's incident, reflected, and transmitted now. And the angle of reflection is still the same, even though not as much of it is reflected, but the angle going through the prism, if you measure from the normal, should be slightly different. And this is where Snell's or Saul's law comes in order to calculate that angle. So we'll need to know the index of refraction of the air, which is about 1, and then the index of refraction of lucite, and then we can measure the angles relative to each other using Snell's law.
So let's talk about refraction. Here's your incident ray. Where's your interface?
The triangle?
This thing, right? This is your interface. So here's the normal. Okay, you can see incident ray, normal, reflected ray. That should follow the law of reflection. But this also has a refracted ray. Okay? And the refracted ray follows a different rule. So remember, at the boundaries between media, you have two possible outcomes. You can be reflected or you can be transmitted. Remember, we did this with string, right? You can be reflected and you can be transmitted. With string, if you went from a heavier to a lighter string, it was different than when you went from a lighter to a heavier string. When you're going through materials, if you're going from air to glass, which one's more dense? Glass or acrylic, okay? So if you're in this case, you're going from a lighter to a heavier string, and then if you go out the other way, you're going from heavy to light, okay? So we know part of it reflects, part of it refracts or transmits, okay? But it turns out the angle of refraction is not going to be as simple as the angle of reflection, okay? So just as a starter, if we have parallel beams, they're going to all refract at the same angle. But if you have something like a point source, they'll all each be calculated separately. Okay. So this brings us to I meant to change this. This guy, Wildebrord Snell, who gets credit for oh no, I forgot the guy's name. Saul something. So basically, Snell gets credit for Snell's law. He was in 1621, and around about 500 years earlier, there was a Middle Eastern guy that came up with this law and published it, but nobody read that, so then he didn't get credit, and now we all say Snell. But Snell doesn't have a cool picture, and we don't have a picture of the other guy. So I'll get you his name. He is important. He's from the golden age of Islam, and he didn't get credit, so I've been meaning to replace him. I just read about it over the summer, so we're gonna replace Snell with that guy. But yeah, it's still the same law. So this relates to angle of incidence. It's still called Snell's law, so you have to know that too. But here we have angle of incidence, right? Here's our normal, so we still have the interface, the normal, the angle of incidence measured from the normal. Okay, you can measure the angle of refraction.
Refraction.
Yes.
Reflection, which we're not showing here just for simplicity, but then you also have this angle of refraction, okay? And the angle of refraction, it turns out, is not the same as the angle of incidence, all right? So we also have to start paying attention to these things called N. And N is the index of refraction. If you're in vacuum or in air, it's usually about 1, because air isn't exactly 1, but it's like 1.0000 stuff. Okay, so we can usually call it 1. And then if it's anything else like acrylic or glass or plastic, it's usually greater than 1. All right, so like 1.2, 1.3 to 1.5. Okay? So the law says N1 sine theta 1 is equal to N2 sine theta 2. It's pretty straightforward. And this must be the material that the angle is in. So we don't necessarily say an incidence, refraction. You just have to make sure the angle matches the index of refraction. So if you're on this side, it's this angle, this index of refraction. If you're on this side, it's this angle, this index of refraction. Yes?
Is there any like common ones we need to know off the top of our head, just like air?
You don't have to know any of them but air. I'll just tell you what they are on a test. So it's not like a useful thing to know, but usually they're between 1 and 2. So if you get one, if you like end up with a number that's like 7, you probably fucked up somewhere. Okay. Yeah. So that's Snell's law of refraction, which should probably be like Stahl's law of refraction or Saul's law, or I forget what that guy. Yeah, Ibn Saul, I believe was his name. But yeah. Always write things down, and apparently write them down in English.
No, just write them down so black people can see them.
But
There you go.
I mean, it's just
There you go.
anyway. So refraction, we have a light beam interacting with a glass prism. Here's your incident beam. Here's your reflected beam. Here's your transmit. This is just the same thing, right? So here, if this is your interface, this is your normal. You can see the incident and reflected beam have the same angle. And here's your transmitted beam. That has a different angle from here, okay? Fun fact, if you have 2 parallel surfaces, if this comes in at a particular angle, even if it turns to go in here, it'll come out at the same angle it went in at, because Snell's law just reverses over here, okay? So you'll get back the same angle you started with, which is kind of fun, all right? Yeah, so anyway, when light rays are incident on transparent media, and what do we mean by transparent?
See through.
Yeah, see-through. Light can go through it, okay? They can be reflected or transmitted. Refraction is the bending of light and as it passes from one media to another. Okay, so the light bends. Now, some things to think about, okay? What changes? Because we have that law, or that equation that we use over and over that says V is equal to frequency times wavelength, okay? So if you go from air into glass, does the speed of light change?
No.
Hell yeah.
It does.
Oh yeah, it does. Yeah.
Does it speed up?
Slow down.
No, slow
No,
down.
it slows down. So this changes. Turns out the wavelength changes. Frequency stays the same. Okay, so the speed of light drops. The wavelength gets smaller, but the frequency stays the same. So frequency is preserved across boundaries, but wavelength and wave speed are not. Okay? Okay. Oh, and just as a note on the index of refraction, the index of refraction is just C, what's C?
Light.
Speed of light.
Speed of light divided by V, which is the speed of light in that material. Okay? So speed of light in the medium and actual speed of light, that gives you the index of refraction. So it's a ratio of your light speeds. Okay, so if obviously, can this thing be less than 1?
No.
No, right? Because this is the fastest speed light can go, so this is always slower, okay? So this always gives you an improper fraction, all right? So if you get your index of refraction as half, you also fucked up. Yes?
So C is the speed of light in air.
In a vacuum.
Oh.
3 times 10 to the 8th meters per second.
So that's also an outer space. Outer space is like a vacuum.
Mostly, yeah. Okay, so there's Snell's law. Yeah, anyway, this is Snell's law over and over and over, and I think that's all the time we have. Snell's law of refraction. Okay, and this is Snell's law. So remember, what was the law of reflection? Theta equals theta, basically. Theta 1 equals theta 2, okay? Angle in equals angle out. Now, where do we measure the angles from?
The normal dog.
The normal dog. So here is, what do we call this?
The
Horizontal.
Our medium?
The
These
plane.
are all reasonable answers, but this is the interface, right? This is
that
the interface of two materials, okay? And then we have a normal to the interface, and then we measure all of our angles from that normal on both sides of the interface, okay? So here's our incident ray measured from the normal. Here's our refracted ray measured from the normal. If you measured this angle, guess what? It would be the same as this angle because reflection, okay? So this is Snell's law, and you can see it still relates to angles, but now it includes the index of refraction. And what is the index of refraction?
Speed of light over the speed of the light inside of
The speed of light divided by something slower than the speed of light. So the speed of light as it travels through a transparent media. And what? Not a translucent media, not an opaque media, a transparent media, meaning light can travel through it, okay? Because if you shine light at this desk, you're not gonna have a lot of transmission, okay? So that's where we are with Snell's law, or Sol's law of refraction, as I've decided to call it now. That's the equation. Here's a question. Okay, welcome to class. Click. Okay, so we're not sure. Please discuss this. We'll take a little bit more time. Think about it. We'll vote again. All right. So we're mostly thinking A, some B, some C. So let's go back and look at Snell's law. It's like math. Okay. So that says N1 sine theta 1 is equal to N2 sine theta 2 is equal to actually N3 sine theta 3. Does everybody agree that you can write it that way?
Yes.
Okay. So in general, and so first off, does it even matter what the angle is in N2?
No.
Why not?
because the equality goes all the way.
Yeah, because really, if you take the equation that you would get here, and the equation that you would get here, right, since this angle should be the same as that angle, opposite interior stuff, okay, you can actually cut out the N2 part. All right, so let's just look at N1 sine theta 1 is equal to N3 sine theta 3. All right, so theta 1 is 20 and theta 3 is 10. Right, so N1 sine 20 is equal to N3 sine 10. Okay, if we solve for N3 in terms of N1, let's just say N3 divided by N1. Okay, that should be equal to sine 20 divided by sine 10. Everyone okay with that math? Which one of these is bigger? I don't think we got a consensus. Is sine 20 bigger than sine 10?
Yes.
Yes. So that means this N3 has to be bigger than N1. Okay? But this tells us something, so that's A, right? Just for this question. But this tells us actually something a little bit more profound. Okay? Because as long as this angle is less than 90, okay, that means that as the angle gets bigger, the sine of the angle gets bigger.
Oh.
Do you agree with that?
Yeah, makes sense.
That's how sine works? Okay. So that means anytime you have sine of 20, it's bigger than sine 10. If you have sine of 30, it's bigger than sine 10. If you have sine of 40, it's bigger than sine 10. Okay? What this says is when you have, in this case, when you have this, when this is more dense than this, the angle gets smaller. If this is less dense than this, the angle gets bigger. Okay? So this is an interesting effect that has some interesting results. What it means is if you go from a more dense material to a less dense material, what happens to your refracted angle?
Can be less different? If you do it from more dense to less dense?
So, okay, so if you're like, let's say, just like maybe with some concrete ideas. You go from air to water, right? Is your refracted angle bigger or smaller than your incident angle?
So it would be smaller.
Smaller, right? Going from a less dense to a more dense material, your refracted angle is smaller. So as your incident angle grows, your refracted angle grows, but not at the same rate. Where this gets weird is if you go from water to air, or from acrylic to air, or glass to air, okay? So if you go from a more dense material to a less dense material, your refracted angle gets bigger faster. What that means is before your incident angle reaches 90 degrees, your refracted angle reaches 90 degrees. Well, if you have an interface that looks like this, and this is your normal, and so your incident ray is going like this, and it keeps getting bigger, right? At some point, if your refracted ray is an even bigger angle, it's going to reach 90. What happens when it reaches the interface? Do you have any more transmission?
No.
No. And so that's a special case. And it only happens when you go from something more dense to something less dense. Because in the other situation, your incident angle gets to 90 before that happens. Okay? So you have to put, it doesn't ever like lose the refracted ray until you're at an angle that you can't get refraction anyway. Okay? So this gives us something, here, I'm going to go back to, called total internal reflection.